Okay guys, so today we are going to talk about quadratics, and I wanted to introduce the topic of quadratics by, well, just talking about what they're used for, why we should even bother studying them. So before we do that though, let's talk about patterns, because patterns are always really interesting. And so for example, when I was young, I was totally into patterns. And there's a common pattern that a lot of you may have seen, but maybe not. And I'm just going to write the pattern down. I want you to see if you can figure out how I'm generating this pattern. So I get, let's see here. I get 1, 4, 9, 16, 25, 36. I'll do one more, 49. Okay, there's my pattern. Stop the video right now and just see if you can figure out what my pattern is. Okay, I'm assuming that you stopped the video and maybe you figured it out. So hopefully what you saw was that I was taking the terms 1, 2, 3, 4, 5, and I was just squaring them. And each of these is the square of the terms. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, on and on and on until I get to, well, to this one I get to 7 squared, so I guess it was only 2 ons, not 3 ons. Anyway, so these were all squared numbers. Now, one of the things that we do, maybe you had trouble recognizing what was going on. So one of the things that we do a lot of times when we're trying to figure out what's going on with the pattern, we take the difference between two pairs and we say, what's going on with the differences? Is there any pattern to the differences? So in other words, I'm going to take 4 minus 1 and see what I get. Well, I get 3. Okay, how about between 9 and 4? What's going on there? Oh, I get 5. What's going on between 16 and 9? Well, I get 7. 25 and 16. I bet you're seeing a pattern already arising. Right, I get 9 between 36 and 25 without doing the subtraction. What do you think it is? That's right, it is 11, which means between 49 and 36 we get 13. I see a pattern going on there. So next, I'm going to check and see. I'm going to do this again. I'm going to go find this. I'm going to go look for the pattern again between my pattern numbers. So between 5 and 3, I get 2. Between 7 and 5, I get 2. Oh, hey, between 9 and 7, I get, got it, 2, 2, 2. So that's kind of interesting. Notice how I had this pattern of squares. We started with these squared numbers, and they produced this really nice pattern, 3, 5, 7, 9, 11, 13. And then those numbers produced even a nicer pattern where I was just adding 2, 2, 2, 2, 2. That was really cool. So, what this tells me, what this at least suggests to me, is that there is, when we square numbers, there's a pattern going on, that square numbers that if we find these differences and we find this difference twice, we're going to get this common thread. We're going to get this what's called a common difference. So if I find the difference between, if I find the differences twice, I'll get this common difference. I wonder if that's going to stay true. Meaning, just because it worked for, 1, 2, 3, 4, 5, is that always going to hold? I mean, what if I looked at other squares that were in a pattern? So, for example, let's see here. What if instead of going 1, 2, 3, 4, 5, what if I said, let's just square the even numbers. So I'm going to take 2 and square it, so I get 4. I'm going to take 4 and square it, and I'm going to get 16. I'm going to take the next even number, so 6. I'm going to take 6 and square it, I get 36. I'm going to take the next one, which would be 8. 8 and square it, I get 64. Then I'm going to take the next one, so what was I on? 8, so 10. So 10 squared is 100. And I will do one more because then I'm going to have to pull out a calculator. So how about 12? 12 squared is 144. Okay, let's go and see if we have a pattern to our differences again. So between 16 and 4, it is 12. Between 36 and 16, it is 20. Between 64 and 36, it is, what is that? I am blanking right now. How embarrassing. It is 28. Okay. Between, between 164, it is, how about, let's see, 36? And between 144 Yeah, between 144 and 100, it is, well, that's a nice easy one. That's 44. Okay, now, the last one, right, we're going to, like the last one, we're going to go find the difference again and see if there's again, a common difference each time this time. So 20 minus 12 is 8. 28 minus 20 is 8. Oh, 36 minus 28 is, you got it, 8. 44 minus 36 is 8. Wow, that worked just like the last one, right? So it looks like this kind of pattern, where we look at the difference between the numbers and then we look at it again and we get this same thing added over and over again. That seems to be a recurring pattern when we square things. Now it turns out we can actually prove that that's always the case. That's always, always, always the case. We're going to get this common difference. Now, how do we prove it? Well, let's try it. Let's see what we can do. It's a little more complicated, but I think we can. So I'm going to say my first term in my sequence is n, which means when I square it, I get n squared. So my next term in my sequence would be n plus 1, right? Just like if my first term is 1, the next term would be 2. So if my first term is n, my next term is n plus 1. So I'm going to take n plus 1 and square it. So what do we get? We get n squared plus 2n plus 1. Okay, so now I'm going to go to the next term in the sequence, would be n plus 2. What would that look like? Well, that would be n squared plus 4n plus 4. Okay, let's do one more because I'm about to run out of room. So I can't go as far as I'd like to. So now we're going to do n plus 3 squared, which is n squared plus 6n. That's not an n, that's a 9. I know the difference between an n and a 9. So 6n plus 9. Okay, now I'm going to find the difference between each of these. Now remember, what I'm assuming is that I'm going to find the difference the first time, then I'm going to find the difference the second time, and the second time they're all going to be the same thing. That's my guess, right? That's my hypothesis. Let's find out if that's actually true. So I'm going to take n squared plus 2n plus 1, and I'm going to subtract n squared. Well, that's easy. That's just 2n plus 1. Super easy. Okay, now I'm going to take n squared plus 4n plus 4, and I'm going to subtract n squared plus 2n plus 1. Well, I get, 4n minus 2n is 2n, and 4 minus 1 is 3. Now I'm going to take the next term, I'm going to subtract it, and guess what I'm going to get? I'm going to get 2n plus 5. Now I'm going to subtract these, just like we did before. Well, 2n plus 3 minus 2n plus 1 is, well, that is 2. And 2n plus 3 minus 2n plus 5, well, that is, 2. Now, if we had continued this pattern, again, because I'm on such a small real estate on my screen, I can't do this, but we see. But it really looks like, right, that pattern that we've been seeing over and over again, it occurs here. So in other words, it looks like when we have these squared terms, there seems to be a pattern that emerges, right? There's this same pattern over and over and over again. Now you're probably wondering, why in the heck are we talking about this? Right? We've been talking about factoring and things like that and quadratics, and yeah, okay, so this is kind of a quadratic, but you said this applies to the real world, and we study it for the real world. Why do we do this? Well, I'll tell you why we do this. Let's check. So anyway, a couple of years ago, I went to New York, and I was at I went to the Empire State Building, and here's the Empire State Building. I think it's pointy, so there's a little point. I don't know what it looks like. So there's my Empire State Building, and the Empire State Building happens to be really high up in the air. It is, so according to Wikipedia, right? According to Wikipedia, it is 1,250 feet high. 1,000, that's really high, right? That's super high. Anyway, of course, I was really curious about something. So what I did, there's this thing that you should never, ever, ever, ever do, right? So I'm just going to tell you right now, don't ever do this, but one thing that people used to like to do is they used to like to drop something from the Empire State Building, right? And I don't know why, because you can't see it, right? Like if I drop a penny, the classic one was always a penny. Like if I drop a penny, I'm not going to see it fall. I'm going to see it fall for a little bit, and then it's just going to disappear. But anyway, so I dropped this thing that had a GPS chip in it, right? And what I did is I looked at it at certain different intervals. I had it give me its distance from the ground after every second. Okay? So here's what I got. I'm going to give you a table. I'm going to make a table of what I got. So, if you don't mind, I'll call T is my times, and we'll say H is the height from the ground. So, remember, at time zero, let's put in time zero in there. That's kind of always important. So at time zero, as you know, it was 1,250 feet up in the air. Okay. After 1 second, so I get the GPS thing, sends me back the information, and guess how high it was? It was now 1,234 feet after I had dropped it. So it's been falling, it falls in the air, and after 1 second, it's 1,234 feet. And now I check it at 2 seconds. And where's it at? Well, it is at 1,186 feet. Yep. And then I check it at 3 seconds, and it is at 1,106 feet. Check it at 4 seconds, it's at 994 feet. Okay, I'm going to keep on going for a little bit. So, checked it at 5 seconds, it's at 850, not 860. It was at 850 feet above the ground, and checked it at 6 seconds, it's at 674 feet above the ground. And then I got bored, right? Like, I seriously thought it was going to hit the ground after 6 seconds, and it didn't, and so I got really super bored, and I was done with that experiment. So, anyway, then I looked at these numbers. So, I wanted to let's look at these numbers and see if there's any pattern going on to these numbers. So, let's check and see. So what I'm going to do is I'm going to look at it slightly differently. Well, I shouldn't say that. Okay, let's go see what's going on here. So we're going to go find the common difference. We're going to go not find the common difference. We're going to go find the differences again between each numbers. So between the first two set of numbers, right, between 1,234 and 1,250, we get a distance of 16. I'm not going to worry about positives and negatives right now. I'm just going to list the numbers themselves. Okay, so I get 16. So now between the next two pairs of numbers, 1, 2, 3, 4, and 1, 1, 8, 6, I get 48. Between the next two numbers, I get, so between, 1186 and 1106, I get 80. Between the next two, I get 112. Between the next two, I get 144. And in between the next two, I get 176. Is there a pattern going on there? I don't know. They're such big numbers, they're kind of hard to digest. So I'm going to do it again, right? So far, I've always been doing it twice. Let's do it again. So I'm doing it again. 48 minus 16, well, that is 32. 80 minus 48, oh, that is 32. 112 minus 80, oh, that is 32. 144 minus 112, that is, you got it, 32. Between 176 and 144, that's 32. So guess what? That distance, those numbers that we got, that's a quadratic. So in other words, a quadratic models a falling object. It models an object based on its time. So a quadratic models it perfectly. And that's one of the big reasons we study quadratics. So we're going to play with it more, but that is the introduction. That's kind of one of our big motivating factors. See you next time.